Welcome everyone. And so I'm in Warsaw in a very unusual setup, speaking in front of my two computers. Um, Surprisingly, it gets a bit more difficult, a bit more stressful if you do it this way, but I hope we can manage. And as I said, today we'll be speaking about Hazelcast and the interesting parts. So probably most of you, or at least some of you, are aware that what Hazelcast does. It's a cache, right? But if you dig inside, you will find a lot of interesting stuff that's worth speaking about. And even though I use Hazelcast in production myself for some time, I was indeed surprised with what you can find internally. And that's what I want to show you today. And I hope you will find this at least interesting. If not, if even if it's not something that you will just go to production with immediately, still as engineers, you should be able to benefit just by learning certain concepts and at least exploring internals. So having said this, my name is Grzegorz Piwowarek. I'm from Poland. I work for um, Hazelcast, as you can expect. Other than this, I'm writing a blog called forcomprehension.com. You can find me doing trainings, and you can find me on Twitter and other socials using the pretty much the same handle everywhere. But since we have only approximately 50 minutes, let's go straight to the subject. Um, Hopefully, I'll be able to answer some of your questions during the QA. When I did this talk last time on a local drag in Poland, it was a freeform one. It ended up lasting almost 2 hours, but 50 minutes is enough as well. So Hazelcast is a company that was the idea that was born in 2008 in Turkey. And just as you are aware or not, it was supposed to be a simple caching solution. The idea was to make something dependency free, very simple and easy to use. One of the core pillars or ideas of Hazelcast founders was that the tool that you're trying to use, if you're experimenting with a new tool, it should be very easy to start with. If you can't start playing around with a new tool and try it out, it's not worth trying it out. So the idea was born for a cache that's simple and distributed. But that was in 2008, and over 12 years, a lot have changed. So we started as a cache, but over time it developed to something called an IMDG, in-memory data grid, which is not only a cache, but actually an in-memory computing platform that does way more stuff than just caching. Naturally, you can use it just for a simple cache, and many companies do that. But there's much more to it. So if you compare the previous picture with the current one, the ecosystem developed a lot. So you not only have Java clients, you have clients for like most of languages available out there. You have integrations with popular frameworks. Plus, a lot of other functionality was exposed by the Hazelcast IMDG itself. It's not a caching anymore. So if you have a look at all the possibilities and data structures available inside, that gets quite overwhelming because, well, it was supposed to be a cache, but actually it's all of that you see in front of you. But we'll go straight to this, and I will show you the most interesting parts. Over the time, naturally, the company grew a lot and got a lot of clients, mostly from insurance, gaming, and finance. Because naturally, if you call something an in-memory distributed low latency platform, that sounds like something that finance would be interested in. And that's the case because London Stock Exchange, Dow Jones, Visa, MasterCard, or even Domino's Pizza, they all rely on that. Other than this, you can see that Hazelcast actually partners with other technologies and provides interesting integrations. So it's not only a computing platform, but in some cases, you might not even be aware that you are using it. But let's go straight to the point. So IMDG. What does it actually mean? So let's try to dissect the name and see what each word means. So in memory, that's pretty intuitive, which means that the computation are happening not in a persistent storage, but somewhere in a volatile memory. What are the benefits of doing that? Usually, if you look at the memory hierarchy, the computations that are happening at the in-memory or RAM space are the fastest out there. So the why that it's being put in the name is to emphasize that that's something that's going to be computed very fast. And you want to use it for stuff that you want to be computed very fast. Data, as you can expect, that means that some data will be stored or processed. And grid simply means that there are multiple processes working as a single group. It's a bit similar to a cluster, but there are tiny differences in semantics, what grid and cluster means. And the first major important information for you to know. So Hazelcast can support two basic architectures. So you can use Hazelcast as a Java process embedded in your application, or you can use it in a client-server mode. Embedded means that pretty much you add a library to your code, you start it up, and it's the part of the application. But in the client-server mode, you have a server, you have a cluster running somewhere else, and you just connect to it using a dedicated client. As simple as that. Other than this, if you've heard about caching, naturally it will support like very popular cache access patterns, which is read through, write behind, and a near cache. So if you look at the very popular architecture, like one of the most popular architectural solutions, you'll see that it can be used in a few modes. Read through means effectively that you have a server running, the cluster running somewhere in there, using a custom loader, which loads data from a database. But then, just like you see on the diagram, hopefully, if you reach out the Hazelcast cluster, if you reach directly to the Hazelcast cluster and not to a data store, and if there is a cache miss, if you don't find the data in a cluster itself, it goes to a database and takes it out. So in this solution, the cluster stays in between the data store, the data source, and your application. Write-through is a bit similar idea. In this solution, you put the Hazelcast between the data store and your application, so that whenever you want to put something into a cluster, and the cluster itself puts the data in a database. But this is where it gets slightly more complex, because those two might seem like pretty similar solutions, right? You put Hazelcast in front of data store and an application, just reading and writing. But look, if you read from a cluster that reads from a data store, you are effectively adding a bit more latency to that, because you have a network trip between an application and a cluster, and then from a cluster to a data source. It doesn't make sense, right? You lose, but it might cost a bit more. But this is where it gets interesting when you go for the write behind. Write behind and write through, they look effectively the same from the architectural point of view. The difference is that you never actually write synchronously to a data store. So you speak to a cluster that serves as a cache, and that's all. And cluster by itself, it asynchronously puts all the data into a data store. So this is pretty much like the most popular solutions that you can see, and use cases where you use a simple caching. Sometimes, even if you have a data source, if you have a cluster of cache between your application, sometimes it's not enough. Sometimes you might think that you might want to squeeze even a bit more performance from that. Then you introduce the concept of near cache. So you can have actually data stored locally, cached effectively before you put it in your cache. But that's a bit, let's say that's enough when it comes to the where you can put Hazelcast and how you can use it. Let's see actually at some more interesting like code and examples. So the very interesting stuff is that the Hazelcast itself is just one dependency that you can add to your application. It's just one artifact containing pretty much the whole solution, including the client itself. You add one dependency and you are pretty much ready to work. Pretty much, it doesn't have any dependencies. I mean, it has minimal dependencies. Some of them actually can't really be avoided, like JSON core or snake YAML. It doesn't make sense to re-implement your own YAML parser. In these cases, we shade all of that and giving you effectively a dependency-free jar. So if you add it to your application, you know that it won't make your application break because of some dependency conflicts. Well, unless you have other Hazelcast dependency, but that's another story. And it's very easy to start with. So if you want to start playing around with the embedded cluster, you just call one method, Hazelcast.new Hazelcast instance, and here's your member running, and you can interact with and play around with. But if you want to play around with a client itself, you want to connect to something that's running already, you go for the Hazelcast client, new Hazelcast client. But look, they both return the same Hazelcast instance, and they implement the same interface. So it's very easy and convenient to switch between different topologies because, well, effectively, the client just delegates all the operations to the cluster, to the member running somewhere else. So you can seamlessly switch between those two solutions, which I always found really, really cool, because in local development, you use an embedded instance, and then you can just immediately go for the connect to, and you can just use all the same code to connect to a remote cluster. Naturally, if you want to connect to since as you probably noticed already, Hazelcast is a solution implemented in Java itself. It's effectively just a Java process. But you still want to connect and operate with other clients. And this is why we have a binary client protocol, which any client, any programming language can adhere to. And once you do this, there's no problem. You can easily speak with Hazelcast and receive and send data over. And if you really want to try to use it, it's very easy, because if you get your instance already or a client, you get a map or data source or something that represents a key value store which acts as a cache, and you interact with it just like with a simple Java map. So in order to be able to use it, you don't need to know anything more than effectively just a basic contract of the map interface. And as you can see, it not only doesn't only have the custom interface. It also has it implements actually the map interface from Java. So you can literally use the same interface. And this is where it actually starts getting interesting. Because from your point of view, if you interact with a map from Hazelcast, which might trick you into thinking that it's just a simple in-memory data structure, you might be thinking that this is what's happening, that you just get and put stuff into a map. But actually what's happening is that underneath, if you have multiple instances, there's a cluster getting formed, which redistributes this data over multiple partitions, over multiple members, and also takes care of actually making copies and distributing them over the cluster itself. So this is where the magic is really happening. But the real reason why I wanted you to be here, I didn't want to speak too much about the caching itself, because the caching is probably you are aware that Hazelcast is able to do that. But the thing is, The Hazelcast is much more, and even with the whole ecosystem. So usually when people start discovering the tool itself, they discover the map interface or some integrations, and that's all. But if you have a look at the whole API, this is not just a distributed map or distributed cache. You have a tools like a multi-map. You have a tools like replicated map, which is a non-partitioned map, where the whole map gets replicated over each member. Whereas in the most popular common scenario, normal map just gets partitioned and then distributed over the whole cluster. Not only maps, but you also have simple sets, lists. Okay, yeah, that's pretty easy to understand and pretty kind of expected. But other than that, you get structures like queue and a topic, which means that it's actually quite convenient to send updates, to use the cluster as a simple tools for notifications or just simple pub-sub. Naturally, it's not something that will compete with RabbitMQ or Kafka. That's not the point. But if you need a simple way to redistribute updates, a very fast way to redistribute updates over, let's say, different nodes of your application, that's a very easy and convenient tool to use. So, for example, one of the integrations that we have is an integration with Hibernate, where you can use Hazelcast as a second level cache. And there are two possible integrations you can use. One is, well, you just use a distributed map. The second one, you use a local map, but whenever an invalidation or some change happens, you redistribute the update using a Hazelcast topic and send them to other members so that they can invalidate or change entries in their own local maps. So this is a real use case for that. But map and data structures, it's also just the beginning. You can find much more than different implementations of the data structures. So imagine now that you store a lot of data in a map, like a lot of it. And then imagine you want to process some of the data. Let's say you want to, well, increment every integer stored in a map. Okay, but if a map is a relatively small size, it's not a problem because you can just, you just iterate over a whole map. You do a map for each and just update it. Okay, but guess what? If you have a cluster formed of 1,000 members processing like the numbers of volume of data that consists of numbers that I can't really name properly, that probably won't work, just fetching all of them and actually processing on the spot, especially given the fact that there's new data coming all the time. In such case, this is where the real in-memory computing starts happening, because you can use something called an entry processor, which means that you delegate the operations itself. You delegate the computation to the cluster itself. So if you want to process somehow an entry, it doesn't make sense, or the whole map, or every entry, or some subset of entries. It doesn't make sense to actually pull them to your local member to do the processing. It makes sense to tell cluster, you do that because you have the data close to yourself and you know how to do this efficiently. And using something like an entry processor, you can actually distribute and delegate the computation to the cluster itself. Okay, let's start digging even deeper. If you start digging deeper, you'll find interfaces like Executor Service. And you've probably already noticed that custom implementations of Java data structures and Java interfaces in Hazelcast, they are prefixed with a letter I. And Executor Service is effectively a distributed executor service where you can actually run certain operations in. So if you want to get something executed, on the cluster itself, you can delegate it using Executor Service. This is actually used a lot by the Hazelcast itself internally, but at some point got promoted to a public API. But if you want to run jobs on a cluster, there is a dedicated solution to this, and we'll get to this briefly at the very end. Okay, another example. Imagine that you have a really, really big cluster and you want to calculate some aggregation. Let's say you have a cache or the in-memory data structure containing the data of your employees, and you want to know what's the salary as a sum of all their salaries. And again, if you really wanted to do this properly, at least in a consistent manner using a simple Java list, you would need to probably, if you want to have a consistent result, apply some heavy locking block, somehow block the data structure from getting updated, iterate through it, calculate, and then get the value. Of course, that's not doable if you have 10,000 members in a cluster with huge volume of data. Again, but in this case, you get a direct dedicated tool that you can use to achieve that. In this case, as an aggregator, you can say that you want to aggregate data using this particular strategy. And in such case, aggregator, as you can see, in some cases, it might feel like using a stream API, like with reduce methods, just a bit more heavyweight, because you can't do this really with a simple Lambda expression, because this aggregator implementation needs to go to a cluster. Okay, so you know that you can have multiple data structures. You can not only use it to store data, you can process it. You can use distributed implementations of an executor service, but you can also run SQL predicates and queries against the map. Naturally, that's not full-blown SQL. Those are just predicates. But if you, let's say, if you are interested only in a subset of values that you store in your cluster, you can do this because you get to write your own custom predicates, which is very handy because, again, taking all the employees from the whole cluster, thinking about numbers of, like so many zeros I can't even name, and then filtering it locally would be very inefficient. So yet again, you can delegate all the job to the actual cluster so that you receive only what you asked for without a need to do all of this by yourself locally. And that's not all. This is where the real fun begins. So if you've been ever into distributed computing and distributed systems, you probably heard about CP theorem, which is like the most basic restriction of one of the basic laws of the distributed computing, and one of the most important requirements that you need to keep in mind, because it's a limitation imposed by physics. It's not something you can really avoid. So, and what does it mean? If you have the distributed system, it can have three properties: consistency, availability, and partition tolerance. But the CAP states that you can choose only 2 out of 3. What does it mean? If you have a few nodes speaking to themselves over a wire, over a network, if you send a request to any of them, you need to make a choice. You can either the whole system can act as available or consistent. It can be both. Imagine hanging out, going with your friend to a club or to a bar on Friday evening, once the pandemic is over. Imagine that you go there, you spend some time together, and then you say bye to each other and you go away. But at some point, one of the batteries just dies. And imagine having a wife of someone calling the other person. And now you need to make a choice because you can't contact the other one. So you either choose to stay consistent or available. So you either don't answer at all, or you answer and say the truth, which means I don't know where that guy is. And the same happens in distributed systems. So the Hazelcast itself, the cluster by default is AP, which means it chooses availability over consistency. So we introduce the cluster in general to get more, squeeze more availability from your system. But sometimes, what if you wanted to be more of the consistency side of things? This is where the CP subsystem comes into play, which is just an amazing piece of engineering. And those are effectively just a distributed implementations of Java concurrency primitives based on the Raft consensus algorithm. Which means that if you use the CP subsystem, you get consistency guarantees for it, which you don't get with normal basic standard data structures. And if you use stuff like that, it means that you have implementations like atomic reference or atomic long, and you can distribute them over your cluster. And the result will be always consistent for the price of availability. However, there are certain limitations. So if you want to use the standard data structures like IMAP IQ, you can have any arbitrary number of members to form a cluster. But if you want to use a CP subsystem, you need to have at least 3 members. Because if you think about this, if you have 1 member, well, you can't really, it's not distributed. If you have 2, if they both disagree with themselves, if there's a data conflict, there's no way to solve it because, well, there's 1 against 1. But if you have 3, you know it will tolerate at least 1 failure because there will be always 2 to outvote the broken or an outdated one. And if you have a look at the internals of Hazelcast and those more expert tools to play with, you will find implementations of semaphore, countdown ledge, atomic reference, atomic long, all based on the Raft algorithm and working in a distributed manner, providing consistency guarantees. And this is like, for me, it was huge to go inside and see how can you actually implement an atomic long or countdown ledge that works, is distributed over the whole cluster while maintaining consistency. And don't get me wrong, this is not something that you should often use in production. I hope your systems are simple enough that you don't need to use that because it's kind of demanding. But even if you don't need that, you should probably still have a look internally how it's implemented because you can grow as an engineer if you read that code. But yet, that's not all. There's still more and more coming. So besides CP subsystem and AP system, you get a lot of advanced data structures which go much more beyond, simple data structures, aggregations, queries, and so on. And one of the first data structures, which is a distributed ring buffer, which is effectively just a form of a list with a fixed size. And if you write to such list and go over the length limit, it starts overwriting from the bottom, from the oldest elements. That hence the name, the ring buffer. You just write all over the place and replace the old ones. Other than this, you get something as interesting stuff as HyperLogLog, which is a probabilistic data structure. So a very simple use case. It's just a simple thought experiment. Imagine you have a very big cluster, once again, and storing millions, billions, trillions of elements. What if you wanted to estimate the cardinality of a data set? Well, cardinality is a fancy word for just number of unique elements. Again, you would need to probably freeze the whole structure and do a lot of iteration over all elements, which is going to be hell slow. But luckily, there's maths that come and statistics that come and save us. So the HyperLogLog algorithm is a data structure that allows you to, well, find a number of unique elements in a data set, but it does it very fast with low memory usage and The answer is not always correct. I mean, it will most likely not be correct, but will be just slightly off. So naturally, this will work for really, really huge data sets, and it will give you answer really, really fast. So that's something really cool. Plus, definitely go and read about the algorithm itself and see how it works. It's also very tricky. But it's amazing that something like this actually can be found in Hazelcast itself and used. Another cool idea is that you often find sometimes there is a need to generate an IDs, unique UUIDs that are unique for the whole cluster. You know, the way sometimes the way the unique identifiers are generated, sometimes if you generate them independently on multiple machines at the same time with similar timestamps, sometimes you can end up with repeating IDs more often than you would normally expect, which is like never. You expect unique IDs to always be unique, but it sometimes can be not the case if you spawn like a lot of like 100 or 10,000 machines and using some timestamp based techniques. But Flake ID generator is something that actually guarantees you the unique identifiers along the cluster-wide unique IDs. And it gets safe even in a split brain scenario. For those of you that don't know what a split brain is, sometimes if you have a distributed system or distributed cache, if you lose connection between some part of the cluster, it will still, well, they can't talk to itself. Okay, the cluster thinks that it lost some of the members, but at some point it can reconnect and have some stale data. And if you have this conflict of two parts of the cache having stale data and not being able to resolve it, that's what you call a split brain. So flake IDs are safe even in such use cases. But that's not all. Maybe you've heard about conflict-free replicated data types. And this is also what you will find in Hazelcast internals, because the Hazelcast provides an implementation of the CRDT PN counter. PN stands for positive negative, which is kind of similar to atomic lock, but it's conflict-free and again safe, even if you lose the communication between cluster members. Hence the conflict-free in the name. And again, I hope you really don't need to use this in production. I hope your systems are simple enough that you don't need to use that. But if you need to, it's here to assist you. But I would still have a look to at least learn and see how it works internally, because you can learn a lot. Other than this, there's quite a lot of interesting integrations going on all around the place. So as I mentioned earlier, there is an integration with the Hibernate 2LC, which is a second level cache. So I think one of the talks before me actually spoke about Hibernate and second level cache briefly. But just to remind you, Hibernate has concepts of kind of two caches. It has the first level cache and second level cache. First level cache is effectively what objects sit in the session. And second level cache is something that, I mean, in the normal flow looks like that Hibernate looks up in the session. If it doesn't find an object there, it goes to a data source. But in front of this, you can put the second level cache. So Hibernate would go to a session. If in session there is no object, it would go to a second level cache. And if in the second level cache there is no data, then it goes to a data source. And this is how you can use Hibernate. You can use Hazelcast with Hibernate as a second level cache provider. And as I said, there are two ways of making it happen. The one way, you just use a distributed map as a storage. But the second one, which is a bit way more performant for like heavy read intensive applications, is that you store the data inside a member internally, but you just distributed updates to other members using Hazelcast instead of just storing everything in the Hazelcast itself. So this is pretty cool. If you ever used Axon framework, which is like the out-of-the-box solution for CQRS and event sourcing, I believe by default it uses Hibernate as well. Sometimes you might have trouble scaling the application, but this can turn out pretty handy if you actually integrate the distributed caching solution with Hibernate within Axon itself, because this effectively gives you, even if you can easily have a storage for your aggregates distributed, highly available, which lets you redeploy your application, your members easily without really losing access to cached aggregates that are built from events stored in an event log. Another interesting one is that, as you've seen, the Hazelcast itself is a Java process. It's not a database, but we have a Spring Data Hazelcast integration, which means that you can use all your favorite repository annotations and get effectively all and write methods and get the implementations auto-generated by Spring itself, which allows you to access your data from a cluster in a bit easier manner. The newest integration that comes to play, that actually I personally implemented fully from scratch, is the integration with Quarkus. And again, if you've seen one of the previous talks, you probably already know what Quarkus is, which is a new framework from Red Hat, which is fully GraalVM native, which makes things a bit tricky to integrate. However, you can use a Hazelcast client with GraalVM and Quarkus, and it will work pretty much out of the box if you add the existing extension. It gets also quite interesting if you realize that you can use tools like Hazelcast for as a session manager, as a session storage for Tomcat, for example. So if you want to replicate all of your HTTP session objects from Tomcat and have them accessible by all your Tomcat instances, you can use Hazelcast for this. In this way, if one of your application, if your Tomcat instance dies, and let's say the load balancer redirects your HTTP request to another instance, from user's perspective, from the client perspective, it's transparent because the Tomcat accesses all the stores of the session data in the Hazelcast cluster. So that's pretty convenient. The same concept is used in the Apache Shiro. Apache Shiro is a security framework, but it uses, again, Hazelcast pretty much for session management and all the security operations. And one of the the newest options, integration, which is not yet merged, it should be pretty fast, hopefully, is that you can use Hazelcast with Envoy proxy, where I think I messed up the slide, sorry. So integration with Envoy proxy, where you can use the Hazelcast as a caching provider for Envoy. Other than this, Hazelcast, as I told you earlier, is supposed to be simple and easy to use and configure. It's not that easy for very complicated scenarios, but stuff like auto discovery and zone awareness, you get pretty much very easily out of the box with our integrations with AWS, GCP, and Microsoft's cloud. What does it do is that if you use the integration, if you deploy something to an AWS, and it can be a simple EC2 or an ECS Fargate or the ECS over EC2, the auto discovery works, which means that the integration will itself look up the AWS API and try to auto discover other instances that you have in there. What's more, if you turn on the zone awareness, that's something that will actually make sure that the cluster will be formed from instances deployed in multiple zones, just if you need a bit more availability, just in case. But If you really don't want, if you don't care, and if you don't want to manage your own cluster, configure it, there is a product from us called Hazelcast Cloud, which effectively means that we do all the work for you and just give you access to a cluster. So whatever you want, whatever the size, but all the responsibility falls on us to actually maintain and manage it. So that's pretty convenient if you don't have an in-house experience, or you don't really want to grow one. You just want to outsource and make sure that it works. But that's not all, because what we covered so far, that's effectively just the free features that you get in the open source version. There's naturally enterprise features, which gives you stuff like stream hot cache, which is effectively just making a way to making sure that your cache is always hot, which means it's up to date. So think Debezium, think change data capture. If the change happens in your database, the change is propagated to a cache and sent immediately. In normal caching scenarios, usually the cache is driven by an application. You go to a cache, and if you don't find something, then the cache goes to a database and fetches the data. But in this case, using the hot cache pattern, the cache is always updated using the events coming from a data source, which is pretty convenient if you want to squeeze a bit more predictable latency from your cluster. There are naturally solutions like that for very big customers that really want to be really available. So we have something like automatic disaster recovery failover, which means that you have your production cluster, and somewhere else you have a backup cluster, and it can seamlessly, if something goes wrong with the first one, it can seamlessly go to the recovery one, which is of naturally which contains, let's say, replicated data from the first one. There are also some very big customers that really want to have, multiple. They really need to have a replication between multiple data centers. There are clients that have data centers in London, California, Japan, and they want to all stay in sync. In this case, there is an option to have a WAN replication, and clusters can replicate data between themselves. We also have Solus integration. So if you really want to be really sure, you can also distribute updates using a persistent broker. Another cool thing is that, if you think about it, the Hazelcast is a Java process, which means it can share some pains that a typical Java applications share, which is, for example, the excessive latencies created by the garbage collection. So if you want to kind of avoid this, there's a concept of HD memory, which is effectively an off-heap store for Hazelcast. In this case, the Hazelcast members store the data on the off-heap memory regions, which stay outside the jurisdiction of a garbage collector, which allows it to squeeze a bit more predictable latency. But the same feature is also used for the hot restart store. So whenever you want to restart a member, usually if you restart the Java process, you lose all the data. But if you use hot restart, the same HD memory will be used as a temporary storage of data. So before the restart, all the data will be dumped into some piece of into a memory that will stay there between a restart. And once the node gets restarted, it just recreates its state from that memory dump, which is, again, very convenient if you want to squeeze a bit more predictable latency when restarting your members. And this is where it gets really funny, because we are supporting what Intel Optane DC persistent memory offers. Persistent memory and Intel Optane DC is effectively just a persistent RAM memory. And this can even speed up all the further processes, the hot restart even more. When it comes to the future, this gets really interesting and really exciting, because we announced recently in March that actually there are plans of implementing the full-blown SQL engine for IMDG, which means that you won't be limited only to just using SQL predicates that I've shown you earlier, but you will be able to use the real SQL against Hazelcast IMDG, which is quite amazing. But that's been announced. That's an early stage. There's development ongoing. I will let you know once we make progress. But that's pretty much it when it comes to the IMDG part. But at some point, I told you that if you want to actually delegate a lot of work and perform distributed computing on your cluster, sometimes IMDG might not be the right tool for you, because if you want to perform some jobs like streaming and aggregations over real-time streaming, IMDG won't be the ideal solution for this. This is why we built something called Hazelcast Jet, that you might have heard about this, which is a streaming solution, like think Apache Spark, Flink, or similar. And there's a common misconception that this one works actually only with Hazelcast. And to be honest, I believe that myself, but that's not true. It's a streaming solution that has multiple connectors that you can use, pretty much connect to message brokers, databases. You can use it with DBZM. You can stream files. You can connect to sockets or even socials, IoT devices. And then you can process the data in real time using pretty much any available operations that you can think of. And then output it again, either to IMDG, any messaging, databases, files, applications, generate alerts, events, or feed just some analytics engines and stuff. So this gets quite powerful, but that's the talk about IMDG. And if you try to use it, it might look like effectively building a quite complex stream API pipelines. Just don't get tricked into that, because it looks like a stream API pipeline. But this is something, if you create a pipeline, that's not something executed locally. That's a pipeline definition that gets submitted to a cluster, which gets executed on the cluster itself. So by doing this, you effectively schedule jobs to be done on a cluster and not locally. And if you're really curious about how does it work internally, Hazelcast Jet started a very interesting, exciting initiative recently, which is they started publishing the architecture and design documents online. That's pretty fresh, but if you want to see how it's done internally, how it works, what's the architecture of Jet and distributed computing, that's all available out there. Internally, when we develop features, we usually start with technical design documents, which means that if you want to introduce a huge change to your cluster, to the IMDG, like a SQL, usually you first start with an idea, you come up with a plan and a design for that, and it gets reviewed. And all those documents now get published online. So if you want to learn more about why certain decisions are made, where are the trade-offs, that's where you can go and find it. There are not so many out there because it's quite recent, but you can expect more and more getting published. Okay, and let's say you want to learn how those tools look like, how to use all of that. This is where you can go to traininghazelcast.com, where you effectively get some free courses. Well, not fully free, because you need to submit your email in exchange. But you get access to courses, which there are not that many of them, but successively there will be more and more added. So if you want to have a deep dive, just go there, get some courses, and learn how to actually use IMDG, streaming processing, security, and distributed concurrency. Again, we are an open source company. The main project is open source. And we really try to encourage people to contribute and help. And if you really want, if you find it exciting, if you find it interesting, well, what's inside and would like to help and see, and you don't know really how to start, there is a guy on Twitter that will help you with that. If you go for this handle, he will gladly explain and help find some tasks for you to get started. We also did some of these people actually ended up in our recruitment processes and now are working with us. So that's one of the ways it can end with. And that would be all from me. So if you follow the URL and the QR code, you can find the talk already. I hope you liked it. So the idea was to get you interested, to see, well, what's inside. I hope I made it happen. I believe that's a really interesting piece of technology worth looking into, even if you don't need it in production. And I really hope that you don't, because I really like easy, simple, straightforward, and predictable systems. So thank you very much. And well, go to my blog and check my Twitter. Thank you.
Thank you for such interesting talk, Grzegorz. And we already have the comment in the chat and the question from Andrei Rodionov. Great respect to Hazelcast due to cooperation with Jepsen. It means that you can trust this system. And the question is, are you planning to have GraalVM native images for Hazelcast?
That's a really good question. So we are also thinking about this internally. I'm afraid that not. So there are two reasons for this. One of the first reason is that Hazelcast internally, it uses a lot of features that are not GraalVM supported. So often the way the members communicate between themselves, they might sometimes use Java serialization, which is at the moment not supported by GraalVM. So this is a big bummer that we can't do this. The second one is that if you look at Substrate VM and the GraalVM itself, you will, for example, see that the garbage collector they use, I mean, it's a single-threaded, fully stop the world, and it doesn't really fit our model and how the data is stored and represented. So the point is that we don't really feel that much that there is a need to prepare a native image for the members themselves, because at the end of the day, we want to provide performance and convenience and not a really small binaries. And if we go for GraalVM, there will be trade-offs to make. But naturally, but the client works with the client works with the GraalVM, so that's good. But no plans for the members for now. I mean for the server.
And the again comment from Andrei Rodionov, it will be a new one GC soon. Guys,
that would be
please,
interesting. I didn't really see that the new one was going on there. I think there is a high performance GC available in the enterprise. But definitely, if there is a new one and better one, definitely worth revisiting if possible. And we are also thinking about redesigning, redoing some of the serialization mechanisms that we use internally. So it might happen, but probably not for now. It's not very high on the priority list.
Okay. Thank you for the answer. And guys, please, if you would like to join the conversation with Grzegorz in Zoom room for questions and answer, use the link below the chat. And Grzegorz, one more thank you for your talk.
Thank you.